All right, here's 6.5, central limit theorem. Basically, central limit theorem tells us that a population with any distribution, the sample means will approach a normal distribution as the sample size increases. It's a really key concept. Basically, it means that as you increase the sample size, you should end up with a normal distribution from basically your samplings, or basically getting the sample means. So pretty neat. Yes, it is the procedure in this section forms the foundations for estimating population parameters and hypothesis testing. The whole point, though, is that as you increase the sample size, any basically distribution will become like a normal distribution, behaves that way. So the random variable x is a distribution which may or may not be normal with mean mu and standard deviation sigma. Simple random samples of all size n are selected from the population. Samples are selected so that all possible samples of the same size n have the same chance of being selected. Yes. Conclusions, the distribution of the sample mean, right, x bar, will, as the sample size increase, approach a normal distribution. The mean of the sample means is the population mean mu. The standard deviation of all sample means is sigma over the square root of n. So some of the practical rules. For sample size n larger than 30, the distribution of the sample means can be approximated reasonably well by a normal distribution. Obviously, as n goes larger, you'll see it becomes even more so. In fact, if you're going to look, when we see the student t distribution, you'll see once you get an n, basically degrees of freedom, basically very large, you'll notice that the values at the bottom of the table were very similar to a normal distribution. And right now, it might not make any sense, but I'll show you that in a later video. 2, if the original population is normally distributed, then for any sample size n, the sample means will be normally distributed. So in other words, if you have normally distributed data and you sample from it, the sample means will be normally distributed as well. The mean of the sample means, you'll note that mu of x bar, in other words, the mean of the sample means is equal to mu. So that's just kind of notational sake, make things a little easier. You might see it just dropped into mu. The standard deviation of the sample mean is sigma over the square root of n. It's often called the standard error, okay? So here's a normal distribution. This is one sample, or basically one sample size in each one of them. And you see as n goes larger, it's becoming more centered at 3.5, right? So, and if you use a uniform, right, uniform's flat across the board. As you go further along, you notice that it becomes a normal distribution as well. Do U-shape, same thing happens here. So, important point, as the sample size increases, the sampling distribution of the sample mean approaches a normal distribution. So, 2 things we can do for applying the central limit theorem. First one is individuals. When working with an individual value from a normally distributed population, basically use z-scores. Z is equal to x minus mu over sigma. If we want to do sample of values, in other words, with a mean from some sample or group, use this adjusted standard error, basically the sigma over the square root of n, when you want to do a group calculation. And here's an example to illustrate that. Suppose an elevator has a maximum capacity of 16 passengers with a total weight of 2,500 pounds. Assuming a worst case scenario in which the passengers are all male, which means they're probably heavier, right? What are the chances the elevator is overloaded? Assume male weights follow a normal distribution with a mean of 182.9 pounds and a standard deviation of 40.8. Find the probability that one random selected male has a weight greater than 106.25 pounds. So obviously we're going to use probably just the standard z-score for that one. B, find the probability that a sample of 16 males have a mean weight greater than 156.25 pounds, which puts the total weight at 2,500, exceeding the maximum capacity. So here's the first one, right? Just a standard z-score, negative 6.5. So basically, again, remember you're thinking mean greater than. So what you want to do is you sketch this out, put your mean down, put your value that you're testing, the next value, and then figure out whether it's greater than or less than, right? If it's greater than, you shade this way. If it's less than, you shade that way. And then that's the area that we need to find. Once we find our z-score, we go and put that on our table. figure out that basically the area to the right of this is 0.7422. In other words, there's about a 74.22% chance that the weight, that they have a weight greater than that. So now, the other one is a sample of 16 males, so it's a group. So we need to do a calculation adjustment for basically the standard deviation of that group. And so you'll see negative 2.611. And you'll see that the distribution looks more pointed. Basically what it means is that with negative 2.611, this z-score corresponds to 0.0045 from the left, which means the probability of it being greater is 0.9955. In other words, about a 99.55% chance, or you can think of the probability that the mean weight is going to be greater than that. So there's a very good chance the safe weight capacity will be exceeded if it's full of 16 males. Kind of a small nuance, but it's good to note the difference. Like this is individual and this is group. So if you ever see a group, think that way. All right, introduction to hypothesis testing. So rare event rule, right? I keep bringing this up time after time, 0.05 or less. We're gonna basically kind of make those values as being our cutoffs for rare events, right? This is the correction for finite population. There's a note, just so you guys know this, except for a couple exercises at the end of the section, most all the examples though, assume the finite population correction factor does not apply, okay? It's just something to be mindful of if somebody asks you about something like this. And that's all of 6.5.